For number 2, we want to find the dimensions of a right circular cone of maximum volume having a slant height of 4 feet. So the picture is given for us, right? But the goal is to maximize the volume, okay? And then the variables, right? We're going to say, well, h represents our height, r is our radius, and v is volume. And now we need a function. So the volume, and I'm just labeling these letters so you can see where they rank on the checklist. You don't always have to write the letters when you're doing this. But the function is, since I'm maximizing volume, I'm going to start with the volume equation for a right circular cone. So I've got 2 variables here, and I have to reduce it down to 1 variable because we're not doing related rates. We're actually doing optimization here. So I want to see, is there a second relationship between r and h that I can use? And that's why the slant height is important, because what we have here is a right triangle where h is the height, r is the base, and 4 is the hypotenuse. So I have a second relationship that says, well, r squared plus h squared equals 16. So I can either replace radius and solve for height, or vice versa. But since I have an r squared here and there's an r squared here, I can solve this for r squared and come back to my volume equation and replace r squared with 16 minus h squared. Before I take the derivative, oh, sorry, I forgot a pi. Some of you are probably screaming at me. It's 1/3 pi r squared h. So before I take the derivative, I'm going to clean this up just a little bit, and I'm going to say, well, this is pi over 3 times 16h minus h cubed. So this is a little bit easier for me to take the derivative of than in this form. So now I'm going to find my domain of this function. So the domain, I want to find the bounds on h. So if r gets really, really small, then the slant height, remember, is fixed, and that would just become the height, right? Because this guy would just rotate in and become smaller. So the biggest this could ever be is h. The smallest the height could ever be is 4, and then the radius would become 4, because this guy would fall down, right? And you would just get a flat circle with radius 4. So we can actually say the height is between 0 and 4, and we could make the argument that at 0 and 4 you would either get a line at 4 or a circle at 0 and no cylinder, so, or no cone. So we're actually allowing the possibility of no cone to be an option here. If you wanted to make this an open interval and say, well, it's got to be between 0 and 4, that might be okay as well, but this problem totally allows for no cone to exist. So what we're going to do is, we've got our domain, and if we write this in interval notation, we're using the closed interval method. So now I'm going to find the critical values by taking the derivative of v with respect to h. So pi over 3 stays out front. The derivative of this inside piece is just 16 minus 3h squared, and this is what we're going to set equal to 0. Pi over 3 is never going to be 0, so I only have to set 16 minus 3h squared equal to 0. So 16 over 3 equals h squared, and plus or minus the square root of 16 over 3 gives me h. So now we do a domain check on these values. Well, we're only allowing for positive values of h, so the negative gets thrown out. So the only critical value that I have is positive square root of 16 over 3. Since my interval is closed, the easiest way to check for extrema is to use the closed interval method. So my endpoints are 0. My only critical value is square root of 16 over 3. and then 4 is our bigger value. So we already know when we found the domain that if the height's 0, you get no volume, and if the height is 4, we get no volume. So now we need to plug 16, the square root of 16 over 3 into our volume equation. And when we do that, I get pi over 3 times 16h, so it's 16 square root of 16 over 3, minus this guy cubed, and so that works out to be 16 over 3 times the square root of 16 over 3. This is, in fact, a positive value, right? It's definitely bigger than 0, so this is our absolute maximum on this interval. So the question said, though, come back here, find the dimensions of the right triangle that maximize volume. So now we know the value of h that maximizes the volume. So the dimensions that maximize volume are a height of square root of 16 over 3 feet, and we have to give the corresponding radius. So to find the radius, we actually define the radius as a function of h right here. We actually found the squared radius. So r is going to be the square root of 16 minus h squared. So since my h is a radical, when I plug it in here, it just comes out. So I get the square root of 16 minus 16 over 3. And so I don't really need to cancel it any more than that. I can just leave it the way it is, and I can say that the dimensions that maximize volume are a height of square root of 16 over 3 feet and a radius of square root of 16 minus 16 over 3 feet. It didn't ask you to give the maximum volume. We just had to verify that the volume was greater than 0 on this table. There's one more note I want to make about this problem. You notice if you look at the picture, there was an X on the picture and we didn't even use it. We ignored it. X represented the volume. So it is possible to use a model which is volume as a function of x, right? Where x is the angle. Oops. But just keep in mind, it's really messy. So you could have seen x, you would have had to figure out how that variable was changing, set the bounds on it, and so, but that's a really messy kind of gross calculation, but it is technically possible to do it that way.